Imagine crossing continents in minutes, not hours. This isn't science fiction. It's the promise of hypersonic jets, aircraft designed to shatter conventional speed barriers by flying at Mach 5 and beyond. These incredible machines could redefine global travel, shrinking our world in unprecedented ways. Turning this vision into reality, however, involves navigating immense technical, financial, and regulatory hurdles. Yet the progress made so far is nothing short of revolutionary, pushing the boundaries of aerospace engineering. We are on the cusp of a new era in aviation. The journey to hypersonic flight has been paved with groundbreaking experimental successes. These uncrewed prototypes have already demonstrated the fundamental technologies required for sustained, super-fast travel. They validate the core physics of air-breathing hypersonic propulsion. In 2004, NASA's X-43E achieved an astonishing Mach 10, or roughly 6,600 miles per hour. This scramjet-powered test flight proved the viability of scooping atmospheric oxygen for combustion, eliminating the need to carry heavy onboard oxidizers. It was a monumental leap forward. Building on this, the Boeing X-51 Waverider flew at Mach 5.1 for over 3 minutes in 2013. This test further solidified the concept of supersonic combustion, ramjets or scramjets. It showed that air could be compressed by the vehicle's own speed before burning fuel efficiently. These experimental flights confirm the basic principles, but they are still a significant distance from commercial passenger service. They represent crucial steps on a long and complex development path. Each success brings us closer to the ultimate goal. At the heart of hypersonic flight lies advanced propulsion. Air-breathing scramjets are key, operating differently from conventional jet engines. At speeds above Mach 5, incoming air is compressed and ignited in supersonic flow without rotating compressors or turbines. This scramjet cycle is incredibly efficient at high altitudes and speeds. It eliminates the need for heavy onboard oxidizers, significantly reducing the aircraft's weight. This design principle is crucial for achieving and sustaining extreme velocities. Some advanced designs propose combined cycle propulsion systems. These would use conventional turbo ramjets for takeoff and initial acceleration. Once sufficient speed and altitude are reached, they would seamlessly switch to scramjets or even rocket boosters. Innovative engine designs are also emerging, such as rotating detonation engines. Companies like Venus Aerospace are developing these for their Stargazer M4 concept. These engines sustain continuous combustion at supersonic speeds, potentially delivering Mach 9 performance with remarkable fuel efficiency. The extreme speeds generate immense frictional heating, pushing skin temperatures up to 1,000 degrees Celsius. This demands revolutionary high-temperature materials like carbon composites, ultra-high temperature ceramics, or specialized metal alloys. Active cooling channels are also essential to prevent structural failure. Despite the promising advancements, significant hurdles remain before hypersonic travel becomes commonplace. Thermal management is paramount. A sustained hypersonic flight generates extreme heat. Materials and cooling systems must prevent structural failure at temperatures exceeding 1,000 degrees Celsius. Fuel and infrastructure present another complex challenge. Traditional jet fuel struggles at hypersonic regimes, necessitating alternatives like liquid hydrogen. However, liquid hydrogen demands entirely new storage and fueling infrastructure, a massive undertaking. The sheer cost and scale of development are staggering, requiring billions of dollars in investment. Early ticket prices would likely restrict service to government, military, or ultra-wealthy travelers. This high entry barrier impacts initial market adoption. Regulatory issues, particularly concerning sonic booms, are also critical. Overland, hypersonic flight, is currently banned in many countries due to disruptive noise. This limits viable routes to ocean corridors unless new mitigation methods are approved and implemented. Finally, safety and certification are paramount for commercial rollout. Insurers and aviation authorities require decades of reliability data before approving passenger service. Building this trust and proving consistent safety will be a long and meticulous process. The landscape of hypersonic development is populated by several ambitious prototypes and concepts. Each aims to push the boundaries of speed and efficiency, showcasing diverse approaches to the same fundamental challenge. These projects highlight the global race for hypersonic dominance. NASA's X-43A, an uncrewed test from 2004, achieved Mach 10 using a scramjet. The Boeing X-51 Waverider, another uncrewed test from 2013, reached Mach 5.1 with a scramjet ramjet. Both proved the foundational principles of air-breathing hypersonic flight. Concepts like the A-HIM Hypersonic Airmaster envision a hydrogen-powered scramjet reaching Mach 7.3. Venus Aerospace's Stargazer, M4, currently in development, aims for Mach 9 using a cutting-edge rotating detonation engine. These represent the next generation of propulsion. Hermeus is developing the Quarter Horse and Halcyon aircraft, targeting Mach 5 with a combined cycle engine. These projects are exploring both military and commercial applications, demonstrating the versatility of hypersonic technology. Each prototype contributes vital data to the field. The initial beneficiaries of hypersonic travel will likely be specialized sectors. Military and defense organizations are keen on rapid global strike roles and strategic reconnaissance. Hypersonic cruise and glide vehicles offer unparalleled speed for critical missions. Government and VIPs, including heads of state, diplomats and emergency response teams, would benefit immensely from ultra-fast point-to-point transit. Time-sensitive missions could be executed with unprecedented efficiency, enhancing global response capabilities. Ultra-high net worth travelers, such as CEOs and celebrities, are also potential early adopters. For them, time is the ultimate luxury, and they would likely fund initial routes. This niche market could provide crucial early revenue and operational data. Furthermore, space tourism firms like Venus Aerospace and Sierra Space may offer suborbital edge-of-space flights. These could double as hypersonic transcontinental services, blurring the lines between space travel and ultra-fast atmospheric flight. The possibilities are truly inspiring. Hypersonic jets represent a convergence of cutting-edge propulsion, advanced materials science, and sophisticated digital design. While uncrewed tests have proven the core principles, scaling to safe, reliable passenger service will demand decades of innovation, regulatory evolution, and massive sustained investment. The future of travel is accelerating, and we are just beginning to witness its incredible potential.